This is a quick introduction to pure bending stresses in beams. So when do you have pure bending stress? Basically, you have pure bending stresses in a beam when the beam is only subjected to bending moments and no shear or axial loads. This would happen in a situation such as this one, where let's say you have a simply supported beam with 2-point loads that are the same distance apart from the two supports. And so if you draw the moment diagram of this beam, you would see that it looks something like this. And in this part here, between the two loads, you have constant, pure bending moment. And no shear, right? If you were to draw the shear diagram of this beam, you would see something like this, right? P, 0, and then negative P here. No shear and just pure constant bending moment. This is a classic example of pure bending. There are many other reasons why we would want to calculate bending stress, even if the beam is not subject to pure bending. We would have to combine these stresses with other stresses, and we're going to cover that in future sessions. But in this one, we are just worried about the pure bending stresses. And so the formula to compute the bending stresses in a cross-section, such as this one, the generic shape, the stresses will be going into the board here, and at any point located at a height y from the neutral axis, the stress would be equal to my over I. In the case of a positive moment, you may want to put a negative sign here just to emphasize the fact that when the beam is subject to positive bending, the points that are above the neutral axis are subject to compression when y is positive, and when y is negative going down, then you get tensile stresses on this part. So the formula is the bending moment times the distance away from the neutral axis, perpendicular to the neutral axis, divided by the moment of inertia. So basically the key feature here is the moment of inertia of the cross section around the neutral axis, right? This is the axis of bending that goes through the centroid of the cross section. This point here is the centroid of the cross section, and this axis is the axis around which the bending is taking place, right? This is looking at this from the side, so we're bending like this. And this moment of inertia is calculated around an axis that goes through the centroid and corresponds to the axis around which the beam is bending. And so that's the key feature. We need to be able to calculate the moment of inertia of the cross section around the neutral axis. And that, the formula is the integral of y squared times dA, where dA is basically all of these differential areas that make up the cross section. So if you integrate dA, you get the the moment of inertia contributed by the whole cross-sectional area. So the key feature again, moment of inertia around the neutral axis. That's in the denominator. So if we want to reduce the stresses, we need to increase the moment of inertia. And again, the stresses will vary linearly away from the neutral axis in a straight line like that. Because stress is proportional to strains, then the strains will also vary linearly away from the neutral axis, but they will be the stress divided by the elastic modulus. Okay? What we're going to learn in the future sections is how to calculate this moment of inertia for any section that we want, so long as we have a mathematical description of that cross section.